And now the stage is all yours.
Okay. Thanks to Steve for nice introduction. And it's my honor to be here and to deliver this distinguished lecture series provided by SIGBED. Okay, today I'm going to just talk about some of the work I do and some of the challenges there's still remaining. And it's titled is Towards Higher Assurance Learning Enabled CPS. Oops. So there has been impressive progress in the last several years. I mean, this one, I don't need to say much. Okay, there's control and perception learning and so on. So this was really impressive. The question is, are we there? But the problem is we are not there yet. There has been a lot of sort of problems that you sort of heard from newspapers and sort of the TVs and so on. So Boeing Max had some problem due to human-computer interaction, and Tesla has problem with the perception, recognizing objects, and it's well known that this pandas can be recognized as anything you can make it to recognize, and there has been some other security problems. So there has been a lot of sort of reports. So although there has been significant progress in technology front and machine learning, especially deep neural network front, safety is still not there. Actually, the problem for safety has actually increased. So the question is, how do you make sure the system is safe? And as you know, the cyber-physical system has been a core of the complex applications, okay, which are many different domains. And these domains are also start using neural network as its components. And because of that, I think it's very appropriate for people in cyber-physical system to start considering learning-enabled cyber-physical systems and then consider and how to improve safety or guarantee safety and so on. And if you look at the sort of research growth in CPS, so there has been exponential growth in number of papers that's sort of related to CPS, especially last several years. I believe this is part of due to many machine learning sort of research has been moving into cyber-physical system in the form of learning-enabled cyber-physical systems. And I started a long time ago when I was just studying it in this space. There was very little work, and now there's too much work. And we have a center at Penn, which dedicated for working in the space of cyber-physical system. And lately, emphasis has been safe autonomy. And I'm part of this precise center. And then today, I will talk about some of the work done by my group in collaboration with some of the members listed here. So my beginning to get interested in safe autonomy was sort of the F-110 car. So in 2016, the World ES Week had hosting a competition. This is F-110 car. And my group got seriously involved in this competition. And in fact, my group headed by Rado Ivanov, I don't know whether he is here, won the competition. That was the very first competition. So today, I'm going to talk about some of the design, what I call design time techniques, and then sort of explain why we need runtime techniques and sort of overview view, and then more seriously how to deal with uncertainty. If time permits, I may mention something about medical cyber-physical systems. So first, to design techniques. This is very SIG. This is how we verified safety of learning-enabled autonomous system. So this work was mainly done by Rado Ivanov and Jim Weimer. So this is a neural network. Now, we don't need to explain it much. Okay, neural networks basically have neurons, and then you have this weight and input that's a linear combination, and then that can be sort of you compute some function, linear function, and then to be able to model nonlinear functions, they add activations. They are typically ReLU or sigmoid. Sigmoid is a nicer function in a sense. It's continuous differentiable, unlike ReLU. Okay? So when sort of people also start using neural network for control rather than just writing a code, they just train controller. And reason for that is that when you have sort of input space like LiDAR data, it's not easy to analytically process the data, okay? And also considering environmental factors and so on. And if you have a perception, it gets even more complex. So it's based on vision, it gets more complex. So it's easier to train neural network to control it. The question then becomes, is it safe? Can we assure? How can we assure it's safe? Okay. So if you look at the verification problem involved in learning enabled components, simple ones like F1 and car, there's a controller, neural network takes LiDAR rays and the control, and there is a plant, which is the simple car, and then input measurement, environment and sensor give you measurements and so on. The goal is to verify the car will not crash into walls. There are many existing work. This is a little bit old, but basically there has been a lot of work in neural network verification. It's still going on, and also designing a neural network to be robust. There's robustness analysis, and there is adversarial training to improve sort of make sure that it's resistant to adversarial attacks, and robust training by data augmentation and so on. So there are lots of different techniques. But what we like to do is, it's not just good enough to say the neural network is verified, because it's not clear what it means to verify. We want to say that system as a whole is safe. So neural network safety is not clear. Even if we define it, it's not clear whether how it immediately applies the safety of the whole system. So we need to consider interaction between neural network and the physical plant and verify that the plant is safe over time. Okay? And there are well-known techniques for proving the safety of dynamical systems. Okay, so it's typically you have an initial state and you have unsafe sets that you don't want to reach it, and then you come up with a sort of the reachable tubes and then make sure that it doesn't touch the unsafe set. That's how you prove the system is safe, because it's not going to lead into unsafe state. Okay? So if you take this sort of the F110 car and sort of the driving around the corridor, and then this is car with all these components, okay? And then you can sort of use the reachability tools for systems with the standard controller. If you have like a flow star, de-rich space, and so on, they work by computing some flow pipe based on polyhedrogen Taylor models, and so on. So that's basically how you do this kind of reachability envelope computation, and then make sure that this doesn't reach the unsafe state, and that's how you prove safety. The question then becomes, how do you model neural network as some sort of function that can be verified using these techniques? Neural network is complex nonlinear functions, basically. Okay? Once you figure out how to do it, then you have the neural network controller, and then you have plant dynamics on the bottom, like a plant as your ODE, and then you have a measurement as some input functions and so on. So you can actually sort of model everything as a hybrid system, except it's not clear how to model neural network controller as a hybrid system. But suppose you could do that, then the problem becomes this reachability problem. Okay, so basically, you give an initial state, you want to make sure that its reachable state is the same. Okay. One nice thing about sort of the neural network with the sigmoid is like a dynamical system, dynamic state. Okay, so key insight that we developed, this was observed by Jim Weimer, and then somehow rather made it possible to actually implement it is sigmoid is a differentiable function. So that you can actually model the different sort of differential equation, and then it'll give you this sort of the behavior of a sigmoid. Okay. So the question is now, how, given this knowledge, how can we take a neural network and then convert that into hybrid system? And so initial condition is based on linear combination of inputs, and then you have this sigmoid function started at initial value 0.5, and then it's the differential equation for sigmoid function, and then you do the sort of the actuation, and then you take a transition at time equal 1, and then you update this to the next layer, and then repeat this process. Okay. So basically, if you have a neural network with a k layer, then and then a neuron per layer, then you end up building the hybrid system with k modes and 2 end state. Okay, so each layer become a mode or a state. Okay, and then number of neurons become expanded by 2 because you have the neurons as well as a sigmoid function. Okay? And then once you have that, you can sort of use the Taylor model to approximate sigmoid, and then you get a analysis scalability. So the way we propose to do is you take a neural network, you encode on the left-hand side as a neural network as a hybrid system, and then you compose that with physical plant, which is usually represented as a hybrid system, and you compose them, and then you do analysis using hybrid system tools. Okay? So it basically become, as I said, okay, k layer with the neurons become hybrid system with k modes and 2 end states, and then you have 2 sort of the hybrid node, hybrid systems. Okay, one representing neural network, another representing plant, and they alternate the execution. So when plant is executing, sort of the controllers idles, and then when controller executes, plant idles, and so they just go back and forth, and then you verify the safety. Okay. So this was sort of like was quite useful and quite powerful. So was able to do more than 100 neurons per layer and more than 10 layers and so on. And so it was used to verify many toy examples like mountain car and sort of F-110 car and quad rotors, and then implementation has been updated or improved using sort of parallelization technique and Taylor model preconditioning. So it was able to expand its sort of the capability or the capability significantly. So it's available. So if anybody is interested in playing with it, please feel free to do so. Okay, it's available on a verisig.org. So this was a good start, okay? But this is really the beginning, because as it is, it's still not scalable. If your input space is perceptual, it's like vision-based perception, then it's going to be so much more complex, such a high dimension, it's not clear how it will scale. Okay, so people have been looking at how to do some abstractions and add the probability analysis, as some of Matthew Cleveland has done and so on. But scalability is a big issue. And also, maybe it's better to somehow adapt some of the testing and validation and then combine with sort of verification. This may be the really way to go, because verification itself is going to be scalable, and testing and sort of validation may not be giving you any formal guarantees. If there is some way to combine these two, there will be some interesting sort of research directions to go to pursue. Another challenge is human in the loop, because right now within model human, but then human add uncertainty, and then its behavior in the loop is going to be not certain. Okay? Now people talk about LLM in the loop rather than human, then even it's even more uncertain, and there'll be some hallucination and so on. And how we model it and how we understand its ramification to safety of the system is not clear. So I think there are a lot of interesting problems to consider. Okay. Now, let's switch to something called runtime sort of technique. So assurance verification testing at design time is not sufficient. Okay. So this is the example we had. So this is verified, okay, using this very SIG and so on. So which was nice, okay? Now you put it onto the corridor and it crashes, okay? Now what did it go wrong? What went wrong, okay? So that's the question, okay? So there are many things that can go wrong because when you do this kind of verification at design time, you make a lot of assumptions about its model as well as input distribution, its environment, and so on. If anything is violated, anything is not the way, any assumption is violated, then it can potentially lead to unsafe states. Okay? So many people have taken this problem as out of a distribution problem. Okay, so some aspect is this sort of input space, and out of a distribution problem is you train it in a sort of the car and plane, and then you inference and apply to something it has not seen, like ships, and then it may say it's a plane with this high confidence. What we like to do is say that this is out of distribution and we don't know what to make out of it. That's the kind of things, the out of distribution. So we've been working in this space. So I want to share some of the work we have done and I found very interesting, and hopefully you find that to be interesting. So one is the detection of a distribution shift, or OD, but that is interpretable, meaning that what we can pinpoint it. And the second approach will be something that can do some statistical guarantee on its detection. So motivation is, this is like a simple car, okay? I have a vehicle looking at the camera and then detecting the object in front of it, and then it has a controller trained by reinforcement learning, and then if you see something too close, then it'll turn on the brake and so on. Okay, so here's the motivation. So this has been trained, and then trained with the car, and now you see something which is a motorcycle, and then bam, it just run into it, okay? Because it has not seen motorcycle before and it crashes. Okay? So the question is, how can we detect this kind of a situation? So this is a technique developed by Yahan and Surad Dutta called memory-based OD detector. Idea is you take these sort of the possible images, okay, sceneries, and then group them into something similar. Okay, so this sort of the empty road will be grouped as your empty road, and road with the car will be grouped as road with the car. Okay, so you identify a set of memories that represents the input space, and then when you see your image, and then if you can identify memory, then you say this in distribution. When you see image and you cannot find any memory that's closely resembling to this new image you just saw, then you say this is out of distribution. Okay? So the question is, how do we cluster sort of the images or the input space into groups? Okay? So we use structural similarity index metrics. This was developed by vision people to measure the sort of the how human eyes look at the images. Okay, and then this with this SIM distance metrics, then you basically randomly select the memory and then see whether this memory should be remembered, and then you get the new the memory in the existing system, existing data, and then if it's close, then you say this is good, and then meaning it's close, then it's already captured by this memory. If it's not, then you keep it and put it back, and then try it again later. Okay, so you keep on doing it until you run out of a data point, and then so this algorithm will basically give you clustered set of inputs, where this clustering is some sense unique. In a sense, it's clustering based on existing input element, not just a cluster with some center, which is not a real data. Okay, so this is important to make sure that this is not just defining some ghost data point. Then using this, basically you take an input and then you get compared to the memory and see whether this is sort of some density is less than alpha, then it's the OD. If it is not, then it's in distribution, and then you do this for the window size, and then basically depending on the threshold, you decide, okay, how many has been detected, how many frames has been detected during this window, and then you say this is OD or this is non-OD. Okay? So this technique has been applied to sort of many, to many case studies. Okay, when weather is changing, many people say if it's raining, nice weather, if it's rain or dark, then things may not work. So it's detecting weather change and also detecting some perturbation by adversarial attacks, and then also some missing LiDAR measurement and so on. Okay? So this is breaking example. Okay, so yes, I think this is just weather changing. Okay? And so on. That's the example of weather changing. Oops. So it was able to detect with detectants with very minimum false positives and little false negatives. Okay, and then it's relatively quick. Okay. Another one I want to sort of just illustrate is this is at some point you have the image and then has the image with some sort of the sort of extra shadow added to it. And this is like adversarial attacks to sort of the by tempering physical environment, and then it can lead into crash. Okay, so if you're using our technique, this can be detected. So we done a simulation in the Cara with the 6.4 crash episode, and this was able to detect almost all of them, and then very low false positive rate, and then it's detecting very in advance, so the car can stop it. And one nice thing about this approach was when it's detected as OOD, this is OOD frame, and then it can see which memory is close to this OOD frame, and then use heat map generation to see what is the difference. So it's basically can be used to explain why this image is considered to be OOD. So this is a nice sort of interpretable output. And we have also done for LiDAR systems, okay? And let me just, okay. So this was nice work and it worked quite well. And this approach is quite general. Each approach is sort of you have deep learning classifier and then you do prediction. But this memory-based approach is actually adding some expert domain knowledge to cluster the sets and then come up with a set of memory that's the prototypical samples and use that to do prediction and some sort of identification of close memory for the explanation and so on. So this approach requires expert knowledge, but it's actually allowing to use this expert knowledge to make it more robust and then sort of being able to detect the OOD as well as explaining. Okay? So this works for any classifier. If you are given a classifier, then you can basically come up with a set of memory, and each set of memory, you take this classifier to retrain within the sort of data that belongs to particular memory. So you have, and by in this example, suppose you have 30 different memory, then you train the classifier 30 times with a smaller set. And then when you get the test image, step one is trying to see which memory close to. And if you don't find anything, then it is an OD. If you find it's close to memory 2, then you use memory 2 classifier to classify. And this turns out to improve performance as well. And we have used this approach for many different applications. Something like a second one is this classifier for robust ECG classification. And then also number 3 is alpha DC, some sort of using this to the neurosymbolic model to add natural constraint. So if you train something, sometimes it does not obey the law of physics. Sometimes when you train using reinforcement learning, if your velocity is 0, it can still move. And you can use this kind of memory idea to make sure that that doesn't happen and so on. Okay? And then some other incremental learning, as well as sort of the data generation using this sort of the memory idea and applied to imitation learning and so on. So it was a nice idea. It works, except it doesn't guarantee anything. So we want to be able to guarantee its effectiveness. So this is the idea behind this CODIT, which is conformal out of distribution detection in time series data for cyber physical system, mainly work done by REMNIT. So for the time series data, we want to do it, but we want to have sort of the detection capability. So time series data is you have a sequence of images, okay, and what sequence of some other kind of data, but it's all generated in time sequential manner, and it's important that it is indeed sort of, there is indeed some temporal dependencies. So there are some existing work trying to use or detect time series data and anomalies in time series data, but it's all point-based approach rather than treating point in the point. Next point is there's some time dependencies. It's treating each point as an independent point and try to evaluate the ordinance of each frame. Okay, that's how we did it for memory-based or the detection I just mentioned. But one of the problems is if you look at this sort of pictures here, okay, just skidding a car, any single image, a single frame may be perfectly normal. But the car skidding is the whole sequence of things that's happening. And another thing is, if you sort of the camera is stuck and giving the same image over and over, okay, then something is wrong, it's OD. But if you are doing point-based approach, each frame, although it's the same frame, it may be perfectly okay. So that's not utilizing sort of temporal aspect of the sort of the video or the stream of input for detecting OD. Okay? So it just shows on the right-hand side the existing technique that quite work well. Okay? So we use this sort of the notion of equivariance and the conformal prediction to come up with a technique that has statistical guarantees. Equivariance is basically if you apply some function and you can apply it to the function before it's sort of classified or after classified, and you have this function that can capture whether you apply before or after. So there is sort of the commute in this function, this equivariance space, okay? So if it's if the sort of the function applied, after function applied, your classification is same as before. The function is applied, then it's an invariant kind of thing. So the cat here, in this case, cat will be recognized as a cat, and then one says cat is moved to the different location, it will still be recognized as a cat. You can do it before you move the cat or after you move the cat. Okay? So that's the idea behind this function. Okay? And then conformal prediction is you come up with some sort of non-conformity score, and then using that score, you can compute the p-value. And then depending on p-value, if it's low, then you say this anomaly. And if it's high, then you say it's okay. And this p-value sort of threshold epsilon is giving you some sort of statistical guarantees. This with the background, okay, so you can take this non-conformity score function for coded. This is technique. So you take an image, sequence of image, and then you apply this transformation G, and then you apply to this sort of the encoding, sort of the variation encoding, like sort of the map, and then you try to compare the output of both, and then depending on how much error there is in between, you may say this is sort of an anomaly or not anomaly. And if you're using one transformation, that may be good, but we were able to find that if you use multiple transformation and each transformation will give you p-value, you combine this p-value using Fisher's method, or because they are independent, and then you were able to use the combined p-value and use again epsilon to decide whether something is OD or in distribution. Okay? And this is coded, and this compared to with the other techniques, existing techniques, it's able to do force detection rate guarantee, temporal OD detection, okay, and then and also it can also apply to non-vision data set. Reason I mentioned is there is another nice work based on optical flow-based approach from Vanderbilt, and they work fine. They guarantee force detection rate and capture the temporal OD, but it's only based on sort of the vision kind of a data because it's using open flow. So we have applied this for this sort of the eco-vehicle systems. We use the transformation, that's the speed. So basically take a video and speed up the processing it by 2 times, and then see whether your trained model can recognize it, or you shuffle the video, or you reverse the ordering of video, or you change the period. So first one goes slow and the second goes fast, and then so on. So you use this kind of a transformation together to detect the OD, and it turns out to be very effective. And we also apply to non-video vision-based approach, vision-based, non-sort of vision data. So it's a gate analysis. So using this technique, so here gate analysis data, we use the transformation that's high pass filter, high low filter, low high filter, and identity. And then it was able to detect various sort of the disease that changed the gait patterns, like the Parkinson and forgot the word, and then Huntington disease and so on. And it was quite good. And we didn't have any baseline for this, so we trained a simple SVM to salvage a baseline and then compare with our technique. So these are the 2 techniques for runtime technique. There are many other runtime techniques that we develop and other people develop. So we have developed something called label calibration, okay, how to improve the calibration, and then vision guard is how to detect the adversarial image and the adversarial video, including digital attacks as well as physical attacks. And model guard is trying to say at runtime whether your model you have used during design time is is still valid, meaning at runtime you observe the output from your actual system and then compare with the model to see whether this actual output could have been generated by your model. If it's not, then something is wrong. Maybe your the car has lost the tire, maybe it's a flat tire, whereas you during design, you assume it has all four wheels, or your UUV underground vehicle has lost the fins, it's spinning. So model you have used to predict the behavior is no longer valid and so on. Okay? And then also there's a distribution shift detector. So rather than just OOD detection for single or short images, whether your distribution has changed, if it has changed, then maybe you can use different the neural network trained for different distribution. And then there's a pack prediction sets. Okay, that's rather than giving one element, you give a set of elements. Okay, and then probabilistic analysis and composition and so on. So since I'm running time, okay, so let me try to get to the punchline. Okay, so there are lots of sources of uncertainty. So data uncertainty, model uncertainty, environmental uncertainty, actuation uncertainty, adversity uncertainty, human in the loop uncertainty, LLM in the loop uncertainty, interference uncertainty. Actually, I got this thing from ChatGPT. So ChatGPT was nice enough to summarize all these uncertainty and give it to me. And much of our work is dealing with some of these uncertainties. Okay? So this is what I mentioned about calibration. So some of the calibration is not, some of the confidence that's generated by machine learning algorithm is not, neural network is not calibrated, so it can give you wrong confidence level. So there's a way to calibrate it. And confidence set aspect is rather than trying to predict one element, which can be wrong, it gives you set of elements with high confidence, and then you can even add another level of probability for over the validation set. Okay, so it's similar to conformal prediction. If you know it, you had So here, rather than the generating one output, you generate set of output, and goal is trying to generate set of output that contains ground truth, and at the same time, it's as more edge possible with statistical guarantee. So when you're avoiding the object, so rather than just giving the point location, you give a set of intervals. Okay. And as I mentioned, this is model-based approach, detect model guard, detecting whether your model is still consistent with the actual system. Another one is rather than trying to verify using the deterministic way, everything is probabilistic, so you want to verify using probabilistic model checker to guarantee that probabilistically your system is going to remain safe at this stage. So this is work by Matthew, and he basically does at design time, do some verification with given state. It's going to be safe with a certain degree, certain probability. At runtime, you estimate where your state is, and then use that to compute the level of probability of safety for next 10-step horizon and so on. So it was a very interesting, nice work. Okay, so it has applied to few case studies. Okay. So this is my last topic. Okay. So there are a lot of techniques, but now in order to assure your system is safe, we can get this kind of point tools to have, okay, VeriSig will say it's verified, model guard says your model is valid, and your confidence calibration says your object recognition has so much confidence and so on. But at runtime, you have the system which are using all these components. How can we combine them at runtime to make sure that system as a whole has certain level of confidence? Okay? So that is the idea. This is work by Ivan Ruskin, and Ruskin, when he was a postdoc at Penn, okay, and he continues while he's at, now he's moved to University of Florida. So the problem of this kind of dynamic assurance is we have verified the system at design time. It provides safety guarantee under certain assumption. We have built the various component monitors to monitor the assumptions. And so it gives you confidence and the component is operating as expected. At runtime, we want to put it together and then have the guarantee, system level safety guarantee. So this UUV is supposed to avoid obstacle and also follow this pipeline. So if obstacle is too close, then it'll be not following the obstacle, but when obstacle is far away, it should follow the pipeline. So the key question is how can we assure this thing at runtime? Okay? So confidence composition approach is estimate safety probability of a verified system with a neural net controller at runtime, and verification guarantee hold as long as verification assumption hold, and we can monitor the verification assumptions. So we find the logical combination of a verification assumptions for safety, and each assumption we develop a monitor, and then you monitor it at runtime and then combine sort of the monitor the confidence of assumption holding to get a confidence at the system level. Okay? So example is this pipeline following. Okay, so you have this environment. If environment, so there are assumptions on environment and assumption dynamics, and composition logic is A1 imply A2 and A3. Okay, so A1 is A1. So you need sort of the different sort of the monitoring. So A1 is for obstacle model, and A2 monitor is M2 for pipe scanning and dynamic sort of the failures. So example here is, okay, so your pipeline avoiding is, if the distance is greater than 5, it should be greater than 5. So this obstacle should be away, minimum distance 5. And if it's greater than 30, then you should be following this pipeline. So that's the basically idea. And then A1 is obstacle is far enough. A2 is current tracking of the pipe. And then dynamic is UUV moved consistently with the dynamic model. And with this, so you have this sort of composition logic, and then they come from these sort of monitoring assumptions, okay? And then you can combine them to make sure to see how a system is behaving. So when everything was good, so as you can see, system level confidence is pretty high. When system deviates and starts not following this, satisfying this property, then its level of confidence drops. Okay? So this is a nice, interesting framework. I think Ivan laid a nice foundation, but we really want to see more applications, bigger case studies. So there are a lot of challenging, interesting problems. But if you really assure learning enabled the cyber physical system like self-driving car, and so which involves lots of different components, then there is a way to combine the sort of the functionality or the level of operational confidence of each component into system level sort of safety components. Okay? So that's that. Okay, and then this I used mostly sort of the automotive example, but medical space is also becoming sort of the similar. There is a medical cyber physical system, Internet of Medical Things. All the medical device gets connected, and people want to, we would like to have some autonomy added to such a system, since you have many medical devices that can coordinate with each other and then close the loop in some sense and so on. So people start talking about level of autonomy in medical cyber physical system, similar to level of autonomy for self-driving car. So in conclusion, so there are challenges and research opportunity quite a bit, okay? So one thing I talked about a lot is like detecting OOD or distribution shift and sort of component level problems, but it's not clear whether the component level problem is going to cause the safety violation of the system. So I think we need to elevate this sort of the reasoning from the component level to the system level. And it's not clear exactly how to do it, okay? So I just wrote it as assuring predicting safety of learning enabled CPS under distribution shift, okay? Because not all distribution shift will create a problem. Yes, some may not. Yes, so we need to have a better understanding. Another aspect I haven't really said anything is, so what if you detect something is wrong? How are you going to recover? So this is really important to be able to come up with this sort of the theory or strategy for recovering in real time at runtime while system remains safe. Okay? And another aspect is verification is good and assurance is good, but real system people want to do testing because nobody will believe that you can just verify and just put it into the system and start ready to drive and it'll be safe. Okay? So we need to have a better understanding of how to do testing and the validation at the sort of system level for learning enabled cyber physical system. That system level testing. So many people have been looking at, if you look at self-driving car, there are all these rule regulation, road regulation. Maybe that can be converted into scenario testing and do some sort of testing and coverage. I think it's all very nice idea. It's just need to be systematically studied and integrated and that tied with how to do assurance at the system level. And the other one is, this is a big event, sim to real, what is the sim to real foundations for learning enabled the cyber physical system? Because nobody developed a system and then just build the system and run around. Usually you do simulation, and then when you're convinced, then you actually build it. Now, how can we sort of expedite the process of moving from simulation to real system quickly as well as with guaranteed, so that it can be sort of utilized in sort of the real system development. Sometimes sim to real, simulation has a much simpler model, real system has much more complex dynamics and capabilities. How do we transition from simple simulation to real system while guaranteeing certain aspects? Okay? So this is some of the challenges I see, okay? So acknowledgement here, I have a bunch of collaborators. Once I highlighted red, okay? So second category is people who were PAN, but they left. And third category is student and postdocs still here. First category is my faculty collaborator. Once with red, the ones who provide some sort of slides to me for this talk. Yes, I use their slides. Okay? Maybe I didn't use it properly, but I did start it with their slides. Okay. Okay, that's it. Thank you. Questions?
Yeah, thanks a lot, Prof. Lee, okay, for the wonderful talk. I'm sure, okay, all the audience is learning a lot of things from you. So now we should be able to have time to have several questions, right? So if you have questions, please feel free to unmute yourself, and you can ask a question to Prof. Lee directly.
I have a question.
Yeah, sure. Go ahead.
So,
please.
First of all, thank you for the talk, Professor Yi. So I have a couple of questions regarding the memory-based OOD detection. So I think you also mentioned in the challenges part that, so let's say we detect OODs, what to do after that? So I can imagine that there might be so many false positives. So we should, for example, we can, like the neural network might classify an input as an OOD, while maybe the network should have done just generalization in that case. And so how do you control this trade-off between the generalization and OOD detection?
So I think this is the real problem. Okay, so that's what I mean by this first one. Okay, as you said, OOD doesn't really result in safety violation. So the question is, can we have a better understanding on the safety of the system from this level of OOD or something? Okay? So this is it possible to train neural network that will take OOD input and then decide whether it's going to violate safety of the system or not. Okay? And then if so, then what can guarantee does it? Which always problem is, okay, now how do you really guarantee? Okay? But this is very fascinating problem. I think that's the kind of problem we need to start to look into rather than just looking at the component level or neural network level saying, okay, this is OOD and this is no good. I think how does it affect the downstream? And I think it's more than generalization. It's different, slightly different than generalization. Thanks.
Thank you. I think you are muted.
Oh, sorry. I just wanted to say, okay, any other questions from the audience? Please feel free to unmute yourself.
So maybe I can ask a question. So yeah.
Yeah.
So the question is also about detection part. So maybe the timing requirement for the detection is also very important, not only the false positive, right? So basically, if you find a tag after consequences already occurred, then the result may be useless. So that means in the meantime, we need to consider false positive or false negative. We also need to consider the trade-off between these two metrics, between the timing and also the false positives. Yeah.
No, I think this is a good observation. I think we really need to understand this real-time I forgot to mention Fensing's work on sort of nice work on recovery, but whether when you detect, you have to make sure there's a time to do something about it. Okay, and they have very nice work that for attack detection, the question is, what is the time? And then they come up with the notion of deadline for recovery. So that if you don't do anything, in the worst case, okay, it's going to crash in, say, 10 milliseconds. That means you have 10 milliseconds to be able to do some recovery action. Okay, but then also depending on what kind of text it is, what kind of OD, and so on. So I think this space is quite rich, and there are a lot of possible opportunities here, potential opportunities, but it's just not clear exactly what is the right way of doing it. How can you really solve this problem? So this is a good problem to research.
Yeah, thank you.
Yeah, great. Thanks a lot, Prof. Lee, for this comment. And thanks, Fei, for this good question. So any questions, other questions from the audience?
Hi, this is Ning from WashU. Thanks for the great talk. I'm curious in terms of sim-to-real. When I used to work in industry, we found vulnerabilities in formally verified system because the sim-to-real gap. But recently, when I tried to address this particular gap, I found that it's almost impossible to have perfect physical world simulators. That means we need to make design choices on what to emulate first and what are the important ones. But the moment we make this assumption, it gives adversary the opportunity to undermine our sim-to-real effort. So I'm wondering if Professor Lee has any insight to share in terms of how to pick this.
I don't think I have any insight to this problem. This problem is a real problem. That's why I put here saying that we need some foundational understanding of this problem, okay? But I think you're pointing out there are so many problems here, but that's what people are doing it, industry is doing it, because that's the only way to move forward. And in fact, DARPA has just announced last year about this program, how to speed up the sim to real. So you are supposed to train something using model simulation, and then they'll give you a real platform and see whether you can adapt it in sort of within deadline, 1 day or 2 hours and so on. But if you that's just a functionality aspect, but you are bringing it in this aspect where, does it have some sort of attack surface, it's sort of the revealing because of this. That I think it's an even more fascinating problem. And to tell you, at the moment, I have no idea. Let me put it that way. I think if you have some idea, I'd love to discuss with you.
I think improving the efficiency is probably a great way to expand the search space. So
Right.
thank you. Yeah.
Thanks for the question. Yep, that's really good.
Yeah, thanks, Nick, for the great question. And I think this will basically trigger a lot of interesting research discussion and collaborations in the future, right? So okay, any other questions from the audience? Okay, so if we don't have any other questions from the audience, okay, please join me to thank Professor Lee for this wonderful talk. I also wanted to mention that Professor Lee has very kindly agreed that we are going to, we have already recorded this video, right? I know, okay, I received many inquiries from many of you because due to the time constraint, some of you cannot, some of the researchers, you cannot join today's the talk online, but we have already recorded the video. We are going to post it on the SIGBED the website. So we are also going to send this information to everyone. So please feel free to distribute this talk information, right? This kind of videos to all your colleagues who are interested, right? So please join me. Okay, thanks Professor Lee again, okay, for his wonderful talk. And we are going to continue have our SIGBED distinct lecture series. So next one will be, I think, in the end of April. So we are going to send out the announcement to everyone. Okay. So hopefully, okay, we can see you again. Okay. By the end of April. With that being said, okay, we wanted to conclude today's distinct lectures. Thank Prof. Lee, okay, for a wonderful talk, and I wish you all have a wonderful day.
Thank you very much. Thank you.
Thanks a lot.
Bye.
Yep. Bye bye.